Okay, we're going to look at page 103, and we're going to look at a different way of solving the systems that we've already had. So in particular, the method that we're going to look at today is using matrices, and we're going to be doing something called row operations. So the first thing that we want to write is, what is a matrix? Well, a matrix is a rectangular array of numbers divided into rows and columns. So just array just means it's just like a listing. So we have this big list of numbers in rows and columns. We're going to use a matrix with something that are the coefficients of a system. So these are going to be with entries that are the coefficients of the system of equations to solve for an ordered triple. So each row will correspond to an equation, and each column will contain the coefficients of a certain variable. To augment means we're going to add on to, and so we will augment the constant column after a vertical dotted line. So let's see what that looks like. We're going to make an augmented matrix right now. So our first row goes in the first, or our first equation goes in the first row. We're just going to write the coefficients. So there's really a 1, even though you don't see it. So we're going to have 2, -1, 1, and 5. And so what's happening is the first column is the x's, then we have the y's, the z's, and the last column is our constants, what our equations were equal to. So our second row is going to have, again, we have a 1 in the front here, 1 in the front here. So just those coefficients, 1, 1, -1, and -2. So there will be no variables in this. Just the way that the matrix is organized allows us to know what each column and row represents. So the last one, we have -1, 2, 2, and 1. Now, because this matrix is representing a system of equations, we can do some different things to every row in our matrix, and those correspond to different things that we did to solve this system of equations. So the row operations that we can use, and there's only these 3 row operations, is we can interchange 2 rows. And so if you think about what that means, if you're going to interchange 2 rows of our matrix, that's just putting your system of equations into a different order. You can multiply a row by a non-zero number, and we've done that before. You multiply a row in order to try and make something cancel, and that's okay because it's just using the multiplication property of equality. Then you can add a non-zero multiple of one row to another row, and that's what we did for the elimination, which is really using the addition property of equality. So let's look at this matrix that's down below. It says, fill in the equations that correspond to the given matrices and then solve the system. So the first matrix was found by using something called Gaussian elimination, and it's put in row echelon form. Row echelon form means that we have zeros here and 1s all along the diagonal. That's row echelon form. And we can use the row operations up above in order to put it in this form. But let's see what happens if we're able to go through that process and we end up with this row echelon form. What happens? Well, the first equation will be x plus 2y minus 4z equals -3. Again, this is my x, y, z, and then my constant column, which I should have had a line right there. My second equation, it has 0x, so we're going to scoot over to the y, so we'll have y minus 3z equals -3. My last equation has 0x, 0y, so it's just going to be 1z equals 2. So what's great when we have this row echelon form is our very last equation has only one variable in it, so we can actually solve, and this is actually really nice. If 1z equals 2, well, we really just know that z is equal to 2. And so we can use back substitution to find the other variables, because if you look at the equation right above it, because it was missing x, we can plug the 2 in there to find y. So to find y, we're going to put y minus 3 times that 2 we just found, and that makes -3. So y minus 6 equals -3, add 6, we get y equals 3. So then we're going to take those two and plug them into the very first equation. So I'm running out of room here. Let's do that. We're going to have x is what we don't know, plus 2 times our y, which was 3, minus 4 times the 2, that was our z. It's supposed to equal negative 3. That's x plus 6 minus 8 equals negative 3. Our like terms make negative 2 there. We'll add 2, and so we get x equals negative 1. So if we put these in our ordered triplet, we're going to have a negative 1, a 3, and a 2. We just solved that system. Now, if we look at the second method here, this is Gauss-Jordan elimination. So you would do all those row operations mentioned above and put it in a reduced row echelon form. So reduced row echelon form means, well, I'm going to put my column here to separate my constants. If you notice, everything over on the left side is zeros and ones. And so what they did is still created the diagonal of ones. They still have the zeros below, which is our row echelon form, but they reduced it further by making all of those zeros. And so what's really nice here is with all those zero coefficients, if you look at the very first line, this is just going to be x equals negative 1. The next one will just be y equals 3. And the last one will just be z equals 2 because everything else has a 0 on it. So if we are putting it in the reduced row echelon form, there's no back substitution needed. You don't have to plug anything in. You just did more row operations. So this will be a negative 1, a 3, and a 2. We have just solved the system. So on this next page, it has two systems worked out using those row operations. And so I want to give you a minute to go through these and try and see if you can make sense of it. So you should pause it and read these on your own. Again, they have this starting system of equations. Both of these are identical. On the first side, though, they just use Gaussian elimination, which means the goal is those diagonals with the zeros below, but then it could be any number inside. Now, on the second column, they used Gauss-Jordan elimination. That means they're going to go further. So they have their diagonal of ones, the zeros below, but they also get zeros above. So again, that's Gaussian, Gauss-Jordan elimination. So you should take a minute, again, read through these and try and make sense of it. Okay, so looking at the first method, they rewrote it as the augmented matrix. Again, there's no x, y, and z written in here. Each of them, we know which one's x, y, and z because they're in the correct column. And so the first thing that they're doing is saying, okay, let's try and make zeros below the 1 because we already have the 1. So that's actually where we always want to start, is to put a 1 in there. And then you want to make 0 below. So they started by taking row 2, that's what R2 stands for, and they put negative 1 times row 3. So they're looking at these two rows here, and they're trying to eliminate. So if you have 1x and then another 1x, if you want them to eliminate, you're going to have to multiply one row by a negative. Now, you're just using that third row. You're not actually changing that sign. You're just going to use it and then add. So it's like 2 steps in 1. So if I take row 2, I'm going to do a little side note of that action here. 1, 3, negative 7, negative 6. And I want to add negative 1, negative 4, positive 9, 7. So that was just taking that third row and changing the signs. So let's see what we would end up with. That would be a 0, a negative 1, a 2, and a 1. And you can see that's exactly what they got there. So a lot of the stuff with the matrix, it's really nice to be able to do it mentally or like in your head, but if not, you can always write out what is actually happening, which is what I just did. So then they want to make a 0 in place of that 1. And so again, we're going to do a canceling out. We have all these 1s in our first column, so it actually works out really nice. So if we take negative 1 times row 1 and add that to row 2, so again, I could write out what that looks like. Negative 1 times row 1 would be negative 1, minus 2, 4, and 3. We're just using that guy. R2 is 1, 3, negative 7, negative 6. And we're using them to make this guy. So the notation for row operations always has an arrow pointing to the thing that changed. So in the first operations, we changed row 3 only. That means row 1 and row 2 stayed the same. In this one, we're only changing row 2. Even though we're using row 1, we're only changing row 2. So negative 1 times row 1 is written here. We're going to end up with 0, 1, negative 3, negative 3. And you can see that's what row 2 turned into. Again, row 1 and row 3 don't actually change. We just use them. For the next part, we're taking row 2 plus row 3. Well, why would we do that? Well, let's look. We have the first part of our Gaussian elimination that we wanted. Now we need to make sure we have a 1 in the diagonal there, and then we need the 0 below it. So what we have is already the 1, so yay. So we're going to use that to help eliminate that negative 1 below. So if I take row 2, I'm going to write it down over here so we just see it. And row 3 is 0, negative 1, 2, 1. If we combine those together, we get 0, 0, negative 1, negative 2, which you can see right there. Again, only row 3 changed. So yay, we almost have it. We have created our 1, 0, 0 and our 1, 0. And so the last thing, we did that, is to make sure we have a 1 to finish off our diagonal. Now it shows that we have negative 1, so if I want to change that, I can multiply a row by a number. So they multiplied row 3 by negative 1 to make my new row 3. So you can see it all changed to positive. So now that it's written in this, we say row echelon form, because we did that Gaussian elimination, we now have a much simpler system, and we can use back substitution. So we start at the bottom and kind of work our way back. So if I look down below here, it says, okay, we have z equals 2, so we're going to plug that in to our second equation. So when we plug that in, we're going to get y minus 6 equals negative 3. So then add 6 to both sides, we get y equals 3. Then we're going to take y equals 3 and the z equals 2 and plug them into the very first equation. And so when we do that, we end up 2 times 3 makes 6, negative 4 and 2 make negative 8. Combine those like terms, we get negative 2. Let's add the 2 to both sides, and we get x equals negative 1. So our solution, negative 1, 3, 2. Which was the system really that we were talking about on the previous pages. So we were just showing the row operations really on these pages. So now if we're going to solve this same exact system but use Gauss-Jordan elimination, the steps are really the same to start off with because we want to still create that diagonal of 1s and 0s. So you can walk through the process, and it's slightly different. In this method, the person started by doing something slightly different than what we did on the left side, but it doesn't really matter. It's still going to work out the same. And so if you look at our row operations, the purpose in this first step, again, is to try and create, well, we already have the 1 in the first corner. We need zeros down below. So they took negative 1 times row 2 and added row 3 to that to make the new row 3. So the only thing that changed was my third row here. And so if we take negative to row 2, we can write that down, negative 1, negative 3, 7, and 6, and add row 3 to that, 1, 4, negative 9, negative 7. That's 0, 1, negative 2, negative 1, which you can see right here. So then after that, we need the next 0. So they took negative 1 times row 1. Often you'll use that first guy, one of those ones in the diagonals. And so they said, okay, let's take negative 1 times row 1. That's negative 1, negative 2, 4, and 3. We're going to add row 2 to that. That's 1, 3, negative 7, negative 6. So we have the 0 that we needed. And so this created my row 2. That's what it said. So then after we have that 1, 0, 0, and we have the next one in the diagonal, we need to turn that guy into a 0. We also need to turn that other guy into a 1, and then all the stuff up above it into zeros as well. So let's see what they have for our next step. So they're taking negative 1 times row 2, that's 0, negative 1, 3, 3, and they're adding row 3 to that. And that is actually going to get me 0, 0, 1, and then 2, which is awesome. So now I have my row 1, 0, 0. I have my 1, 0 here, and I have my 1 in that diagonal. So really I just need to get my zeros up above. So they're starting to try and get rid of that -4. You normally want to use the 1 that's in that column to get rid of things. So let's see what that will look like. They said to take 4 times row 3, so that's going to be 0, 0, 4, 8, and they're going to add that to row 1, 1, 2, -4, -3. So we're going to have 1, 2, 0, 5, which you can see here as that first row. So then they're going to work on trying to get the other zeros. And again, the order of this doesn't matter so much, but having the nice diagonal of 1s works to try and make the zeros, because you can turn those 1s into anything pretty easily. So the next thing that we're going to do is multiply row 3 by 3. And so I'm going to show my work down here. So row 3 would be 0, 0, 3, 6. We're going to add that to row 2, 0, 1, -3, -3. And that becomes 0, 1, 0, 3, which you can see right here. And again, that only changed row 2, so keep in mind what these arrows are pointing to. That's the only row that will physically change in your matrix. You're just using the other row to help you out, which is totally fine. So the next thing that we're going to want to do is turn this 2 into a 0. So what they have is taken row 1 and added that to -2 times row 2. So 0, -2, 0, -6. So that's 1, 0, 0, -1, which you can see is right there in the first row. And so when we put it again in this reduced row echelon form, it took a few more row operations than the last problem, but we don't do any back substitution. You can just see your solution set right there because everything else was zeros. And so that's solving a system with matrices. Now this might be totally unfamiliar to you because in previous math classes you might not have gotten to matrices. So try it, be patient with yourself, and just practice. Practice makes you perfect at this. So good luck.